the theory of rare earth, or the Fermi paradox. Enrico Fermi was eating lunch with a few of his co-workers at the Los Alamos National Laboratory in 1950. Imagine them eating and conversing while possibly sipping wine as well. Who knows? The only thing we and everyone else know is that they discussed UFOs at some point. Fermi in particular made a claim that would go on to become extremely well known. "Where is everyone?" he questioned. Extraterrestrial life was the topic Fermi was discussing. The Fermi paradox was built on this query. Learn more about the Fermi paradox and the purported answer involving rare earth elements by following me in this video. The Fermi paradox is the seeming absence of evidence despite the high probability estimations for the existence of alien intelligence. Given that the universe is limitless and that there are countless stars and planets in it, how is it possible that we haven't discovered any other signs of life but our own? Since that luncheon more than 70 years ago, we still don't have a satisfactory response to Fermi's query. We usually try to come up with speculations when we don't have the answers. Many theories have been suggested throughout the years to explain why the Great Silence continues. These hypotheses could clarify why it appears that we are alone in the cosmos. Some of them are upbeat, while others are quite ominous and depressing. For instance, it's possible that aliens are too far away to make contact, although it's also possible that we're the first species to exist and will go extinct before any others. Hibernation theory can be one that makes you feel uneasy. This highly hypothetical hypothesis states that aliens would be waiting and hibernating. But what are you awaiting? Well, if a superintelligent civilization had been successful in replacing its biology with machines, it might be waiting for the cosmos to expand and cool it down so that its computations might run more quickly. In fact, colder surroundings are better for computers. But amid all of these hypotheses, we discuss the idea that planets like Earth are simply exceedingly uncommon in this video. The rare Earth hypothesis is the name given to this theory. This hypothesis basically states that the mix of astrophysical and geological conditions necessary for life and the evolution of complexity are just not frequent in our universe. In other words, we are quite distinctive and remarkable. If this theory were accurate, things would get very messy. Because we believe that the universe is isotropic, astronomy and most of cosmology today assume that intelligent life is prevalent throughout the cosmos. When we talk about isotropy, we mean that on a macroscopic level, the cosmos is the same in all directions. Isotropy can be understood by seeing a sphere. Nothing changes if you stand in the sphere's center and point in various directions. Each of these additionally, it complies with the Copernican principle, which holds that a sample taken at random is likely to be representative of the entire population. The Copernican principle tells us that planets similar to Earth are widespread in our universe if we translate this in the context of astronomy and cosmology. We require this presumption, the Copernican principle, because it would be extremely risky and nearly impossible to do quantitative research on the objects we view, such as galaxies, stars, and planets, if the universe weren't isotropic. To build our mathematical grasp of the world, we require it. If the Copernican principle is incorrect, Earth actually belongs to a class of very few planets and is not representative of the entire solar system. Perhaps Earth is an anomaly. Wouldn't this seem like the more likely possibility given that we haven't discovered any proof of extraterrestrial intelligence in the universe yet? Two theories serve as the foundation for the rare Earth claim. The first is that planetary systems frequently contain microbial life. According to the second, evolved life is uncommon in the universe. Combining these two theories, we can see that Earth may have evolved from a sequence of incredibly rare events and situations, making it a truly unique location. This argument was made in reaction to the biases and assumptions that were found in the Drake equation, which basically says that there should be a lot of intelligent life. The Drake equation's answer has unstated assumptions that need to be investigated, as stated by Ward and Brownlee, the authors of the book Rare Earth. The assumption that life begins on a planet and progresses to ever higher complexity, culminating on many worlds and the emergence of civilization, is crucial. that most likely occurred on Earth. As life progressed from single-celled organisms to multicellular organisms with tissues and organs, culminating in animals and higher plants, it is also believed to have started here some 4 billion years ago. Then they should consider if this specific history of life, which has evolved from simplicity to animal-grade complexity, is an inevitable or even typical outcome of evolution. Perhaps it's just an unusual combo. The Drake equation can be mathematically stated as the sum of several elements. N is the number of civilizations in our galaxy determined by several factors, including our star, the average rate of star formation, Fp, the fraction of stars with planets, Ne, the number of planets that can support life, Fl, the number of planets that will support life, Fi, the number of planets that will support intelligent life, Fc, the number of advanced civilizations, and L, the amount of time it would take for these civilizations to send out signals into space. The number of civilizations in the galaxy is to be determined using this equation. Naturally, our limits on the factors get increasingly accurate as we learn more about the cosmos. For instance, astronomers now estimate that our galaxy has between 250 and 500 billion stars, with the rate of star formation being roughly 3 solar masses per year. Astronomers now have a far better idea of how many stars have planets and how many of those planets are likely to be habitable thanks to the finding of over 4,000 extrasolar planets in recent years. In actuality, a research from 2013 suggested that there may be as many as 40 billion Earth-sized planets circling in the habitable zones of their stars, 11 billion of which would be orbiting Sun-like stars. This estimate was based on Kepler data. The Drake equation is still fraught with doubt, particularly in regards to the advent of life, the rate at which life will give rise to intelligent life, and all that comes after. However, as we already mentioned, Ward and Brownlee had doubts about Drake's theory. They provided a fresh version of the equation in their book as a result. It resembles this in most respects. The Milky Way has around n stars, and on average, each star has about n planets. If we want to get an accurate estimate of n, we have to take into account many different factors, including HZFG, which represents the galactic fraction of stars, HZFP, which represents the Milky Way's fraction of stars with planets, FPM, which represents the percentage of rocky planets, Fi, which represents the percentage of habitable planets where microbial life first appears, and Fc, which represents the percentage of planets where complex life first appears. Even the possibility of extinction events occurring during the evolution of an intelligent species is attempted to be taken into account. These are also subject to restrictions and uncertainties, just like the Drake equation components, but by using Earth as a model and applying the Copernican principle, it is simple to see why it would be challenging to locate planets that satisfy all of the aforementioned requirements. Other particular to Earth characteristics that are thought to have aided in the emergence and development of life were also listed by Ward and Brownlee. For instance, the existence of plate tectonics, which has proved essential to the stability of the climate on Earth. Additionally, they offered geological proof indicating the Earth was extremely cold and covered in ice twice in the course of our planet's existence. Astrophysicists refer to this as snowball Earth epochs. Both of these epochs, which took place around 2.2 billion and 635 million years ago, coincided with significant changes in terrestrial life. The Cambrian explosion, which took place between 570 and 530 million years ago and was marked by an explosion of species diversity and the emergence of nearly all modern animal lineages, occurred at the same time as the later snowball period. To put it another way, major developments in the history of life on Earth seem to have occurred after a snowball Earth epoch. In conclusion, we can argue that the rare Earth hypothesis is uncertain, just like the Drake equation, the Fermi paradox, and all attempts to solve them. This can be explained easily because there is only one planet that we are aware of that supports life. We are unable to create a statistic, thus we are unsure of our ability to communicate with other civilizations in the future. We are highly constrained in our search for life, which may exist in a variety of habitats and chemical circumstances, by having only this one blueprint. it's possible that life in the universe is radically different from life as we know it. The fascinating part is that the Fermi paradox, one of history's most perplexing contradictions, can be resolved with the discovery of just one extraterrestrial civilization. Who knows, maybe all it takes is a little patience and commitment. Maybe one day we'll be shocked to learn that an alien civilization has been found. In the interim, all we can do is wait it out and hope for the best. Here's where the video ends. Thank you everybody for watching. Do you believe that humanity will ever discover the remains of an alien civilization? Please let us know in the comments section below. Don't forget to subscribe, and I'll see you on the channel again soon.